All right, we can go ahead and get started. So the next talk will be by Aswin Vijayan, talking about the properties of massive dusty galaxies at cosmic dawn.
Hi all, I am Aswin Vijayan. I'm a final year PhD student at the University of Sussex, UK, working with Peter Thomas and Stephen Wilkins, studying the properties of galaxies in the Epoch of Reionisation. In this talk, I will explore a few select dust-driven properties of massive galaxies that we observe in the FLARES suite of simulations. I would also like to bring attention to some of the people that I'm working with as well. Christopher Lovell, Peter Camps, Martin Bass, UC Casisto, Will Roper, and the extended like Eagle and Skirt development teams. So probably this would be the last FLARES talk until we meet at another conference, I guess. So Will and Chris talked in quite a detail about the FLARES simulation. So I think I'll give an even briefer introduction. So we simulate a range of overdensities from a big dark matter only box. So our aim is to get some of these massive galaxies in the Epoch of Reionisation. We re-simulate them with the very successful Eagle simulation physics, which was tested, and it produced a really good match to the observations that in the local universe. So our aim is to test the Eagle physics at the higher redshift, namely the Epoch of Reionisation. So I'll give like a small primer to some of the properties that I'll be discussing here, namely two. So when studying the high C galaxies, the infrared excess UV continuum slope or the IRX-beta slope is a relation that is widely used. So this is used to usually estimate the attenuated or the obscured properties from the UV observation of galaxies. One such relation that was calibrated in the low Z universe was the starburst relation found in for the starburst galaxies found in Muir et al. 1999. So they show like a really tight relation when you plot the IRX against the beta, and this has been used to to get the dust obscured fraction in many of these high redshift studies. Another one is the dust SED temperature. This is used usually in modified black body fits to obtain the infrared luminosity and then get the infrared excess. So for example, recent work show an increasing value towards high C. So you can see on the right a plot from Bhavans et al. 2020 paper, which shows an increasing dust temperature, which is and a fit was obtained for observations found across redshifts. So I'll move on to give an introduction to some the galaxy sample we are using. So we only use some of the massive galaxies that we have in the simulation, basically anything greater than 1,000 star particles approximately. It corresponds to around 10⁹ in solar mass. We have a peak star formation rate closer to 1,000 solar mass per year. This can be seen in this plot I have shown on the right, which is plotting the stellar mass against the star formation rate. And you can see that we have a really good statistical sample of massive high C galaxies. And with this, we hope to study some of the dust-driven properties. So how do we generate the SEDs? So we use the publicly available radiative transfer code, SCRT, to produce the full SEDs. So we use a prescription which is quite similar to what was done in CAMS 2016 and TRIFOR 2017 with some modifications. Similar to that, we model young stars and birth clouds using the mappings 3 templates and old stars using BPAS. We fixed the DTM ratio for different galaxies from this fitting function we obtained from previous work we did with the L-Galaxy simulation, the semi-analytical model, trying to model the evolution of dust in galaxies. We also use an SMC type of dust distribution, which is supposed to be applicable to high C galaxies. We do not take into account AGN emission on the SEDs, and we do not calibrate to any of the observations. On the right, I have shown a sample SED from a galaxy at redshift 8 with approximately 10 raised to 11 solar luminosity in the infrared. We also had a different model that we presented in the previous paper, which uses a line of sight dust extinction model, and it is quite flexible and much faster than running a full radiative transfer simulation, not simulation, sorry, post-processing the galaxies with a full radiative transfer code. So before moving on to the properties that I'm going to explain, I'll briefly look at the high C luminosity functions. The first one is the UV luminosity function. So you can see on the right, I show the luminosity function from Z equal to 5 to 10. We are incomplete at the faint end due to the selection of the most massive galaxies. We do provide a reasonable match to the extreme UV number densities. And here is the infrared luminosity function. This one is also incomplete at the faint end because of the selection. It agrees reasonably well with some observations in different regimes. As you can see, there are also some inconsistencies with some of the observations at different redshifts. But one thing that is quite clear, if you look at redshift 5, is that we severely underpredict the number density of extreme infrared luminous source at Z equal to 5. And this is one of the places where, so if you look at this region where two different sets of observations agree with each other and we fail to match up to that. So what are the reasons for this? So this has been studied in other Eagle simulation papers where they show that the SFR function is predicted to be a bit lower in the Eagle galaxies. This was explored in the Katsianis 2017 paper, and we also explored in flares in level 2021, where if you look closely, there is some slight underprediction. And to the to people who have paid close attention to the UV luminosity function, you can see that this is almost similar to that small underprediction we had for the UV LF. Another reason was like a lack of bursty star formation, which was shown in BAS 2020 when he was trying to understand why the infrared luminosity function was unpredicted in the local universe. So another possible reason could be a transition to top-heavy IMF in some of these extreme galaxies. So simulations like SIMBA have shown that you can get better agreement with the sub-millimeter counts. See Chris's paper in 2021, which is due to the higher SFRs compared to the Eagle simulation in SIMBA. But there are also caveats, like you can get this lack of quiescent galaxies as shown in this plot on the right. So what we need is like a fine interplay of feedback and star formation recipes at higher redshift. Maybe we could look for some calibrations at higher redshift as well. After that small detour and explaining some of the caveats in the model that we are using, I'll talk about the IRX-beta relation now. On the right, I've plotted the IRX-beta relation along with some of the observations for redshift 5 to 10. As you can see, the relation from flares follows a local starburst relation, and it is quite well matched to many of the observations that you have at these higher redshifts, with a few low mass galaxies following the SMC-like curve. There's also a few deviations. There are also a few galaxies in the observation that show these low IRX, high beta, but we fail to predict some of these galaxies. We are not sure what the exact reason is. There are other models that have shown the same thing. For example, the FIRE2 simulations produced quite similar results with showing a lack of low IRX, high beta galaxies. I'll look at the dust temperatures. Now, we namely look at the luminosity weighted dust temperature, which is one of them is the peak dust temperature or the peak wavelength at which the infrared emission peaks. We also look at the mid-infrared power law plus the modified black body fit that gives you an SED dust temperature, and also an optically thin modified black body dust temperature, which is used in many of the high Z studies to get the infrared luminosity. So as expected, you can see that the peak temperature is much lower compared to the other ones, and the optically thin one lies somewhere in the middle. So we predict for the peak dust temperature, we predict a relation which has a higher slope than compared to lower redshift relations like the ones which was shown by Liang et al. 2020 from the massive fire simulation, as well as the local redshift relation found in Schreiber et al. 2017, I think. And we see that the massive galaxies here follow a relation which is which has a much higher slope. We also failed to predict some of these really cold galaxies, cold dusty galaxies as well. Yeah. So here is the prediction for the dust SED temperature. So if you look at the optically thin dust SED temperature median relation, you can see that it is slightly above the Bhavans et al. 2020 relation that I showed earlier, which is also plotted here as this line. So what could it imply? It could mean that there might be the infrared luminosities predicted might be underestimated in some cases. There's also a similar case of this very low dust temperatures being seen in observations, but we failed to pick up some of these in our simulation results. So with that, I conclude my talk, and I probably would we probably could see this on arXiv soon. And we have quite a lot of work going on as well, like testing for bias and cosmic variance, effective AGN, prediction for Euclid and Roman dust continuum sizes, looking at the Balmer break. We also hope that we can do some prediction of the infrared properties from the UV. As Will explained before, FLAIRS 2 is already in development, and we are welcome to any ideas and collaborations. Thanks.
All right, thank you. Get to questions.
Okay, how much is this under prediction of IR luminosity due to missing AGN contribution to your simulated SEDs?
So I have a plot for that. Okay, so here's a plot of that. You can actually see there isn't much of a deviation that is being caused at these. Oh, sorry, I must explain before. So what we did here was we tried to add we calculated the bolometric luminosity that could be obtained from the supermassive black hole at the center, and then added it completely to the infrared luminosity to see how much of a leeway we can have. And we see that there isn't much of an increase in the infrared luminosity function as compared to the stellar only contribution. So the observations lie somewhere around here, and we still don't match up to the number densities.
Somebody would like to hear more details about your dust model.
So the dust model is based in everything is done in the skirt radiative transfer code. The only thing we add is the what should be the dust to metal ratio in the galaxies. Other than that, like choosing grain distribution type is done within skirt, so we do something like SMC. So if you want more specific answers, you could contact me.
All right, sounds good. We probably need to move on. There's more questions in the Slack. You want to check them out there.